Hey everyone, welcome back to another episode of the LlamaIndex Webinar series. Today we're excited to host Victoria Lin from Meta, who's the author of the recent paper, RA-DIT, Retrieval-Augmented Dual Instruction Tuning. So it's a really interesting paper that kind of combines both fine-tuning as well as RAG, and talks about how you can actually use fine-tuning on the LLM and retriever to actually improve RAG performance. So there's a lot of interesting topics for discussion here. I think it's going to be very interesting to just do a deep dive into the paper itself, as well as open it up to Q&A in the second half to kind of answer any questions from the audience in terms of like the paper itself or any high-level concepts about RAG as well as fine-tuning. So without further ado, I'll pass it over to Victoria.
Thanks for the introduction. Hi, everyone. Thanks for joining today. I'm going to talk about our recent paper today, RA-DIT, Retrieval-Augmented Dual Instruction Tuning. So I have been following some of the interesting features LlamaIndex has been shipping. So it is great to join this community today. The paper is joint work with awesome colleagues from Meta. So at this point, if we take a look at the landscape of large-scale language models, in 2023, we are really seeing lots of exciting products being shipped that has touched millions of users. People came to applications powered by large-scale language models and ask for different questions and requests. And we see language models has been functioned as amazing multitask learners to address a different user request, as shown here. Yeah, so basically, what are the limitations of pure parametric language models? So first of all, once finished pre-training, large language models will come with a knowledge cutoff, meaning that it is very hard for them to represent knowledge after the pre-training is done. And second, we have been seeing that language models tend to hallucinate about especially facts that doesn't happen very frequently. And the third is large language models, because they make decisions purely based on their parameter space. So they can, so it is difficult for them to show provenance of attribution for their results. And this really motivates the group of method, which is trying to augment large language models using non-parametric memory. And the most commonly seen nowadays is augmenting them with a vector data store, for example, and the model could retrieve information that complements its parametric knowledge from this data store. So speaking of retrieval-augmented language models, it can even be date before large language models has got popular. So the one seminal paper I want to mention here is the retrieval-augmented generation for knowledge-intensive NLP tasks, which probably motivate the keyword RAG. And here, so this paper came from Meta. Actually, this paper came from Meta AI research. And basically, it proposed to augment an encoder-decoder model with the retrieval component. And the retrieval component coupled with the encoder-decoder model can be trained end-to-end over multiple tasks and show decent results on lots of knowledge-intensive NLP tasks. It is worth mentioning that this model uses the dense the retriever came from the paper called dense passage retrieval, which is actually the first paper that shows that it is possible to use dense retrievers to achieve competitive results in open domain QA question answering. And that actually really motivates the later work, which enables fine-tuned retriever for specific downstream tasks. So another paper that was worth mentioning is the retro architecture came from DeepMind, which is almost right after the introduction of GPT-3 and also the Gopher paper from DeepMind. So this paper basically introduced an external retriever memory during pre-training stage, and the retriever memory and the language model is coupled through cross attention, and basically the retriever and the language model is trained from scratch during the pre-training stage. So what really motivates myself to find like the retrieval-augmented language model domain really interesting is one paper came that at the beginning of this year, which is called replug. So this is a really simple methodology that basically augment black box language models with retrieved content from an external data store. And the paper shows that given a well-trained black box language model and also a retriever, we're able to retrieve information from the data store and just simply put them in the context window of the language model. And that can enable good performance improvement on downstream tasks which require external knowledge. So this really shows that without like implementing additional customized architecture, we're able to leverage retriever to improve the performance of language models. And accompanying this paper, I think there are several concurrent papers proposing similar approaches at the same time. And also, I think within the industry, maybe perhaps people started using this type of application even earlier. So for the replug paper, it further proposed this ensemble modeling approach, where it shows that when we want to integrate multiple passages, so instead of using passage concatenation, which has been shown effective in other works, so this paper uses parallel retrieval augmentation, which append each passage with a language model prompt separately and ensemble the prediction from different passages and show that this performance can also give strong competitive results. So this approach is simple and it leverages off-the-shelf language models and retrievers, and it actually is a strong motivation for our RA-DIT work. So when we were conducting this retrieval-augmented dual instruction tuning, we were basically asking this research question: is it possible to strengthen the coupling of the language model and the retriever in a retrieval-augmented language model through fine-tuning? And this way, we enable the language model to better utilize the retrieval content and also the retriever to be able to return more contextually relevant content for the language model without expensive pre-training, for example. And to illustrate the RA-DIT approach we eventually adopt, it is best to just use this runtime example. So here, suppose the user has issued a language model prompt, and here, like we show a question. And the prompt is issued to both the language model and the retriever. And from the retriever, it typically returns us multiple evidence passages. And what we do here is, following the replug approach, we prepend the retrieved passages to the prompt and further feed them to the language model. We also use this parallel retrieval augmentation approach, and basically, for each of the retrieved passages, we create an individual augmented prompt and feed them to the language model. So we conduct this during both fine-tuning and inference. And notice that state-of-the-art retriever still makes mistakes. So it is possible that the passages retrieved are indeed relevant. It is possible that it only has some shallow similarity with a query, but doesn't actually help with your task, as is shown here. And so for our retrieval-augmented instruction tuning approach, which is conducted on the language model side, we basically take all these augmented prompts and maximize the likelihood for them to output the correct answer. So as shown here, for both the correct and incorrect passages, we maximum their probability to produce the correct answer. And in some sense, we later show that this can basically promote the robustness of the language model against the noise content in the from the retriever. And for the retriever fine-tuning, it is also very simple. We notice that the language model prediction, the probability generated by the language model can also be used as feedback signals for the retriever. So in the sense that if a content is helpful, we hope that it will promote and give the correct answer higher probability. And so this will motivate the other side of the loop, where basically we take the language model scores of different passages and compute a distribution based on the language model score, which we call language model supervised retriever score, which was also first proposed in the replug paper. And then we minimize the KL distribution between the language model supervision signal and the retrieval output probability. And this way, we encourage the retriever to return more relevant content to the language model. So it's a very simple process. And for this process, we show that we can carry so basically in our work, we carry them in independent steps. So instead of like perform any joint training, so we show that we're able to just perform language model fine-tuning and retriever fine-tuning separately, and the combination can still yield further result improvement. By the way, if there is any questions, feel free to interrupt me, and you can just unmute yourself.
Yeah, no worries.
Okay.
For questions, let's put that in the chat, and then I'll go over it during Q&A.
Sounds great. Okay, so so our framework is conceptually very simple. So like I will go through the fine-tuning data sets we use. So I think similar to recent instruction fine-tuning papers we saw. So in this approach, we also conduct multitask fine-tuning. So in the hope that we can promote a general multitask language model after fine-tuning. So for our case, because we do have intentional downstream focus, which is to create language models which performs better on knowledge-intensive tasks. So our fine-tuning dataset selection bias towards two categories of tasks, which promotes knowledge utilization and contextual awareness for the language model. So for example, we select lots of reading comprehension tasks and summarization tasks, which typically comes with a background text and certain decisions the language model needs to make based on the background text. So we think this type of tasks basically by nature promotes the language models to have higher dependency on its content. And also other categories of tasks, which includes like open domain QA, dialogue, assistant chat datasets, and also chain of thought reasoning datasets, which is in the hope to promote knowledge utilization. So we did some like careful task selection when choosing these tasks. So based on like how popular the data set is, which we think is an indicator of like their quality. And also we found that we can use different sets of data set for the language model and the retriever as a DL and DR data sets shown here. So when we are actually doing the fine-tuning, so we also conducted something similar to typically people do in instruction tuning, which is basically using temperature sampling methods to balance the composition of the data sets so that it's not predominated by certain categories. So we include these type of details in our paper. Okay, so in terms of our experiment setup, so because our framework conducts fine-tuning, so we initialize a framework using pre-trained language model and the retriever. So for the pre-trained language model, we use a Llama 1 series. And most of our experiments is conducted using 65 billion models. So for the retriever, we initialized it with a state-of-the-art retriever, which is published actually at the beginning of this year. So it's called Dragon. So it is probably like the strongest performing retriever, like over lots of popular downstream tasks, and it is trained by like some creative knowledge. Some creative augmentation technique for contrastive learning. So like for the details of Dragon, please just check out the paper. And so our fine-tuning is like is a standard supervised fine-tuning for instruction learning. So here we use the label loss, which is basically the language model loss, but computed over only the task output. So we also use a technique such as example packing, and we basically applied attention max so that the attention doesn't so that the attention doesn't go across example boundaries. And for the retriever corpus, we try to use the largest retriever corpus we can efficiently serve to mimic a real world data distribution. But like you can see here, like, so here, in some sense, the retriever corpus we use is not super large. So it is in total about 400 million text chunks. So 37 million of them comes from Wikipedia 2021, and the rest comes from like we sampled from common crowd dumps. So for our fine tuning, basically through the approach I just introduced before, we for each of the fine tuning examples, we will generate three text chunks for it from the retriever, and create 3 retrieval-augmented fine-tuning prompts for them. And for the inference, we conduct this parallel retrieval augmentation in a similar manner as during the fine-tuning time, but instead without further specification, we use 10 retrieved passages. Okay, so I first we'll go through our model performance on several widely used knowledge-intensive task benchmarks. So including MMU, natural questions, trivia QA, and also them combined with a subset of queued tasks. So we can see here that so we compare our model with a base Llama model and also the Llama model just using off-the-shelf retrieval augmentation. So here we see that adding retrieval augmentation is effective for Llama models, both before and after fine-tuning. So we see here that the replug approach is already pretty effective, and it is able to improve the zero-shot performance from the Llama model by a fairly large margin. And after fine-tuning, so we can further and consistently improve over the replug approach in terms of the zero-shot. We also show 5-shot in-context learning performance. And for 5-shot in-context learning, what we do is we prepare the 5-shot examples. We sample them in a similar manner as people do in in-context learning. And for each of the few-shot example, we will add the top 1 retrieved passages from the retriever, and so that we will prepare like five examples with retrieval augmentation as a demonstration. So we see here that so for both replug and RA-DIT, like we still improve over the base model in terms of 5-shot, but we also see that the base model visibly getting stronger here. So which is an interesting observation. And the second is like we also observed that in the few-shot learning setting, fine-tuning is not as effective compared to in the zero-shot setting. So it slightly improved over the replug approach. And I think in our dev set, we also show that on sometimes it can even like slightly lower the performance compared to just a running replug. So regarding this, this has also been observed in previous instruction training papers, that fine-tuning sometimes doesn't significantly improve the model's in-context learning abilities. And I think here, because so the way we prepare the fine-tuning examples, like it is more similar to the zero-shot format. So I think there is a chance that our fine-tuning slightly overfit to that type of format. But all that said, I think like basically investigating like how the dynamics between the in-context learning and fine-tuning plays is an interesting future topic. Okay, so besides the knowledge-intensive tasks, which we kind of expect retrieval to help, so we also examine the model's performance on some common sense reasoning tasks, which is commonly used to benchmark language models. So here we show the performance on a series of them, and we benchmark the performance of our model with both with and without retrieval. So first, we found that our model without using retrieval is actually improves on top of Llama in this common sense reasoning tasks. So this is good news. It shows that, okay, so things match with our expectations. So after instruction training, the model becomes better at answering questions. And the second is that we show that basically after the RA-DIT approach, our model didn't significantly forget common sense knowledge. And we also show that even for common sense knowledge, oftentimes if we add retrieval, the model performance can still be slightly improved. But arguably, the improvement is less significant compared to the knowledge-intensive tasks, which might also be interesting because for common sense reasoning, the knowledge is possibly frequently appeared in the pre-training corpus and is probably has already been memorized. Lots of them has already been memorized by the parametric memory of the model. Okay, so and next I want to show a section of ablation. So to answer the question, okay, we saw some performance improvement. Do they really come from retrieval-augmented fine-tuning, or do they actually just come from fine-tuning itself? So here, basically, we run on a set of development set, so which is models fine-tuned using the RA-DIT approach, and models fine-tuned using the conventional instruction tuning approach on the same set of data. So here, it's worth mentioning. So I think in this set of experiments, we are using the vanilla Dragon retriever. So it's not our fine-tuned retriever in this set of results. And here, basically, we see that fine-tuning, both vanilla instruction tuning and retrieval-augmented instruction tuning actually significantly helps the model in terms of their zero-shot performance. And we see that retrieval-augmented fine-tuning indeed also significantly improved on top of vanilla fine-tuning. So which indicates that indeed we have some, so it matches with our expectation that retrieval-augmented fine-tuning further improve the model's ability to utilize the retrieved content. And here we show that actually we see bigger gaps between the two fine-tuning approaches when we are including top 10 chunks instead of just the top one. So I think later I will show some qualitative results which shows that we think retrieval-augmented fine-tuning will enable the model to both be better at extracting useful information from the retrieved passages and also be more robust against the noise in the retrieved content. Okay, so here is the result I mentioned previously. So for five-shot evaluation, we didn't see significant improvement from both fine-tuning approaches actually, which is quite interesting, I found. Okay, so and here we also show a set of retriever fine-tuning strategies. And so for the retriever fine-tuning, basically we conducted alternatives mainly over what should be the task composition used to fine-tune the retriever. Because actually before our paper, most of the retriever fine-tuning work. So before our paper, most of the retriever fine-tuning in retrieval-augmented language models are conducted over unsupervised text. So I think before this, I think people have tried fine-tuning retrievers on downstream tasks, but in the large language model context, we haven't seen much of the approach. So at the beginning, we were not quite sure whether fine-tuning on downstream tasks is a good choice or not. And during our experimentation, we did found that the story is a little bit complicated. So as the results shown here, so we first had an observation is fine-tuning over our downstream. Fine-tuning over the downstream tasks we collected directly actually doesn't significantly improve on top of Dragon. It is possible due to the task has diversity issue and other things, but we don't see significant improvement. And on the other hand, fine-tuning over unsupervised text gives a small gain. So as you can show from the table, it just improved a couple of digits compared to Dragon. But here is the idea is with unsupervised data, we're basically able to collect a larger amount of examples and basically just having the model to retrieve relevant context to perform sentence completion tasks. And finally, so in our final approach, we found that if we induce a mixture of the unsupervised text and the multitask data, with like a fairly small amount of the multitask data, we can get the best performance. So eventually we use a recipe with like 95% coppers and 5% of the downstream task data. So what are the takeaway from this experiment? So I think after this, like we found that certain things in our retrieval fine-tuning approach. So for example, the language model supervision score we used, there is possibility to further improve that. Sorry, I think just back. My screen just disappeared a little bit. Okay, so yes, I think our lessons, one is like, so the language model supervision score we use can possibly be further improved. And we plan to conduct some like follow-up experiments in that direction. So so we still kind of like believe there is enough potential in just fine-tuning the retriever over a larger collection of downstream data. Okay, so I will also like present some scaling law experiment we conducted. So far, most of the experiments I showed are using the Llama 65 billion models, but we also applied our approach to the 7 billion and 13 billion model. And here, like we show the performance on a set of 6 tasks. There are a couple of interesting findings. So the first one is like from the plot, we can see that overall, overall retrieval augmentation helps smaller models more significantly compared to larger models. So as can be shown, like for example, if you look at the zero-shot relation extraction tasks, so for the smaller 7 billion models, after retrieval augmentation, we can even bring the performance on par with larger models like the 65 billion models. Another interesting finding is the effectiveness of retrieval augmentation varies significantly depending on the nature of the tasks. So for some tasks, retrieval augmentation is very effective, like one-hop relation lookup tasks, such as like zero-shot relation extraction. But for more complicated tasks, usually it becomes more difficult for retrieval augmentation to close the gap between smaller models and the larger models. So for example, hot code QA, and I think we also have ablation results on MOU, which I didn't put here. MOU is also very hard. So like after retrieval augmentation, smaller models and larger models also demonstrate a significant gap. So this is very interesting because it shows that there is something fundamental about parametric scaling. So it's possible that like the reasoning capabilities and other things from larger models is intrinsic to its parameter size and is challenging for non-parametric data store to complement that gap. Okay, so these are the scaling law experiments. And I think overall here, other findings are typically the models will benefit from adding more retrieved chunks, but we can also see that in our parallel retrieval augmentation approach, usually adding more retrieved chunks results in diminishing return, in the sense that like usually we see the largest performance jump in the top 1 retrieved passages, and adding more like usually gives smaller yields. Another interesting finding, which is not very obvious on this set of tasks, is that we find that sometimes the model benefits more from adding more passages. So in the sense that like maybe the task is very challenging for the retriever and the top 1 retrieved results just makes too much mistakes. And in that case, sometimes we just see like a slight performance drop when we use only top 1 retrieved content. And in those cases, we have to basically using 10 retrieved passages to complement each other, and the model performance can be reboosted. Okay, so here is also a qualitative result we have, so which is basically to show like what exactly is the model doing. And here we compare retrieval augmented instruction tuned models and vanilla instruction tuned models. And basically like a couple of takeaway from this table. So one is we found that actually for both models, they still show tendency of being distracted by the retrieval-augmented context. So as the first row shown here. However, so we found that like for the examples we went through, we frequently see that. So for the retrieval-augmented instruction-tuned model, so even in cases it is distracted, usually it will produce the false answer with a smaller probability. As shown here, like the negative log likelihood is much larger for the retrieval-augmented tuned model, and also like in cases where the context is indeed relevant, and the model is able to leverage it to extract the correct answer, we found that the RA-DIT models is typically more confident. So in the sense that it will like extract the answer with larger probability. So this is some interesting finding. And also like by going through the results, we found that so indeed like one important future directions for improving these type of models is somehow we should further improve the stage of like how we conduct retrieval, because like for complicated questions like how to file QA, we saw that for most of the time the retrieved passages is not very relevant, and the model has to be able to cope through the noises from the passages. And another comment is sometimes it's so at this point like we didn't conduct the experiment to check whether for passages, for example, humans decide it's not relevant, whether that's indeed relevant to the model or not. So sometimes maybe like it's just like some vaguely related passages that can encourage the model to produce better answers. We just didn't conduct experiments in that aspects. Cool. So I think with these, I wrapped up the experiment session. And I think, and for this talk, I think the takeaway is that we present this RA-DIT approach, which enhances retrieval-augmented language models using lightweight multitask fine-tuning. And we show that this approach is able to improve the language model, the retriever, and also their integration. So RA-DIT, so in our experiments, we show RA-DIT over multitask instruction tuning, but we think it can also be used to create tightly coupled RALMs for particular downstream applications like maybe FAQ over internal documentation and other things, where particular RAG application is useful. But on the other hand, it can possibly also be blended just with standard instruction tuning approach to create overall better models. In terms of future direction, so I think I have already covered, which is somehow we should still keep on improve the retrieval quality. So for retrieval quality, I just see like open domain retrieval is a very challenging task. So in the sense that the model needs to find the relevant information when we talk about like trillions of tokens of poppers. So this is still a very, very challenging task. And for our retrieval-augmented fine-tuning approach, you can see that for our retrieval fine-tuning signal, in case initially the retriever doesn't return the correct answers, and maybe like if it returns a set of negative answers, it's actually challenging for the retriever to further improve. And future work should so we should like do some smart adjustment on the fine-tuning laws and other things. So another direction is so in our approach, we basically conduct atomic retrieval in the sense that like for each of the examples, we just retrieve using like simple heuristically derived queries, like maybe the question and other things. So, but I think in real world applications, lots of time, if we just like retrieve using the language model prompts, so this makes the problem even more challenging. And I think like, so there are recent proposed works, which is about how do we decompose a problem into multi-step and like retrieve the relevant information. So I think these type of system 2 level retrieval augmented approach is also very interesting. With this, I will wrap up the talk and I will take more questions. Thank you.
Awesome. There's a lot of good stuff in here. And so I don't actually know if we're going to be able to cover all the questions that I also personally want to ask for, and also the audience questions, and I'll have remaining like 20 minutes or so. But maybe we could get started in terms of Maybe we could just like stop the screen share as we go to Q&A.
Sure.
The first question is from the audience, and maybe this is just like on the methodology of like the RA-DIT approach. Is like when you fine tune both the language model as well as the retriever, do you fine tune it independently, or do you first fine tune the language model first with some sort of retrieved context, and then you iterate and then move to the retriever?
Yes, so we fine tune them independently. So like in the sense that like we only conducted, so in our paper, we only conducted 2 steps. So one is when we fine tune the language model, we basically use the retrieved content from the base retriever. And when we are fine tuning the retriever, we use the language model feedback signal from the base language model. So we only conduct these 2 steps. So we do think it's interesting to further investigate whether we can get further gains by just doing this loop in more iterations, but we just didn't do in our experiments.
Got it. The next question I was going to personally ask is like, when you fine tune the language model, you're basically, I think there was a section in the paper that basically says like, you kind of do retrieval on top of this context, and then you fine tune the language model to either use the context or ignore it, right? And so in that sense, you're basically kind of like baking in like information into the language model, right? Because it's like if the retrieved context is actually really bad, you want to have some prior intuition, like, hey, this actually isn't really relevant to the question. Maybe I can surface something from my own like kind of parametric weights, basically. I'm kind of curious to hear your take on how much this is related to the idea of can the LLM like bake in knowledge, right? And kind of how effective have you seen this to be, right? Like what's the limit to which you can fine tune a language model to try to actually just like rely on its own parametric weights to surface information versus the retrieved context?
I see. So I think this is a very interesting question. So I think in some sense, yes, so we did found some like we also discussed in the qualitative result session. We think like the language model has some ability to basically distinguish whether this piece of context is relevant to the instruction in the prompts. But actually, I haven't thought it in a way of like whether that means like the language model has basically recited some of its own parametric knowledge or not. I think, okay, I see what you mean. So I think in the cases where maybe the passage is wrong, and we're still prompting the specific fine-tune the language model to output the correct answer, that could have some effect. So I think, so in hindsight, like when I look back on our approach, I just feel like compared to some of the recent papers, so we did all these very implicitly. So basically, like we say, identifying whether the passages is like is relevant or like when to rely on the parametric knowledge. I think we just did it implicitly through this process of like, regardless of the passage is relevant or not, just output the correct answer. So I think we later eyeballed some examples from Hopal QA, and I saw some significant effect. So in the sense that like I go through the passages, I saw the model has the ability to discriminate. But I think probably my comment is that like I think we just didn't explicitly try to bake in the procedure to inside the model to recite its knowledge like some of the most recent work does.
Got it. Interesting. Okay. No worries. Yeah, that makes a ton of sense. The next question is from the audience. So going back to the methodology in terms of like fine tuning the LLM as well as the retriever, do you have like a separate set of labeled data used to fine tune each one? And maybe the second part of this question is that it seems like when you fine tune the LLM, you split it, or basically you like do one chunk of retrieved context and like replug style. But whereas like when you fine tune the retriever, I imagine you're setting like some top K. So I'm curious like how if you've actually tried fine tuning the LLM with more than one chunk of retrieved context, and two like whether there's like separate data sets for fine tuning the LLM versus the retriever.
Okay, cool. So we do use separate data sets, and the exact data sets is in the table of our paper. So the data sets has some overlap. So we collected this set about, I think, 20-ish tasks. So we eventually use 20 for language model fine-tuning, 20 for retriever fine-tuning. So the reason they are different is because some of the language model fine-tuning data sets is probably not useful for retriever fine-tuning. For example, we have summarization. So that creates a separation. And also in terms of like the actual fine-tuning, so one detail is so our language model fine-tuning is also using top K. But I think we probably use a different K for language model fine-tuning and retriever fine-tuning. So language model fine-tuning is using top 3 passages, and like basically for each of the original examples, this will create 3 corresponding examples for fine-tuning.
Got it. Makes sense. The next question I have is around retriever fine-tuning. Maybe just like, and this is kind of like potentially helpful for the audience as well. The way I typically think about like training a retrieval model just on its own is you're just trying to maximize like, embedding similarity between the question and the context. And typically that's like an information retrieval problem. Whereas here you're kind of fine-tuning the retriever with respect to the loss of the language model. So how in your mind, maybe at a very high level, what are the benefits of this type of approach versus just like fine-tuning the retriever independently? Like what's kind of like the intuition for trying to actually train it to optimize for this like end-to-end loss, and does it lead to cases where it does better than traditional retrieval? I'm just curious. I know that's a lot of stuff.
I think this is a great question. So I think first of all, like I think nowadays we talk about retriever, maybe like instead of similarity, it's more about relevance. So like it's like you retrieve stuff, it's relevant to your content at hand. And I think so I think this is a great question. So I do believe that if we can further optimize a retriever independently, yeah, if I have a much stronger or accurate retriever, I think it can further improve our system. I think here is just like I feel like this approach is probably more data efficient. So I didn't have like exact like experiment data to show, but I feel it's more data efficient in the sense that because like we are fine-tuning the retriever to search for content that we know, it's helping the language model on certain tasks. So hopefully like it's more data efficient to fine-tune the retriever, and also hopefully this way the content returned by the retriever is more suitable for the language model, as well as like the prompts you give to the retriever, because in this case like you give the prompts similar to the language model prompts, versus when you're separately training a retriever, like you probably train on different data.
Yeah, I wonder if one aspect here is, and this is just like throwing it out in the dark, like there's like lost in the middle problems, like if you retrieve stuff and let's say there's context in the middle. And so I wonder if by like optimizing for the end-to-end LLM loss and how the retriever learns to order the context in some way such that actually helps the language model.
I think so. Yeah. Sorry, repeating your question.
That wasn't a question. It was just like a thought, like basically, if the retriever can actually order the context, like by fine-tuning the retriever on the LLM loss, it can order the context in a way that actually helps the LLM or attend to the relevant piece of the context. Because like it's like if you order it in the regular way, there's like lost in the middle problems, right? If there's like kind of relevant context in the very middle of the retrieved context versus at the ends, because the language model tends to attend to like the ends of the context more than stuff in the middle. Anyhow, it was just a thought. It wasn't really a question, so don't worry about it. The next question I was going to ask, and this is from the audience, is between fine-tuning retrieval. I guess this is, and you show this in the experiment results, but like between fine-tuning retrieval and just using like top K from like the base retriever, which one is better? Like were you able to basically just like show an improvement in retrieval performance by fine-tuning it?
This is a good question. So I think we only indirectly benchmark the retrievers in the sense that like we found like in the end of the RALM performance improved on some downstream tasks. We actually didn't separately benchmark. So actually we did. So like so retriever fine-tuning experiments like conducted by my colleague Xilun. So I think he actually did use traditional retrieval evaluation metrics such as MRR. So I think he saw some correspondence that like the retrieval standard metrics will also improve. But sometimes it's a little bit complicated during like the data set ablation, I think. So I think sometimes we found that because the mismatch of the retrieval fine-tuning data set and the downstream tasks we use, yes, sometimes like you can see like a non-correlation. And yeah, so I think at this stage, I still feel that like we kind of should be a little bit careful about the retrieval fine-tuning task we use so that the retriever doesn't overfit to a certain type of things.
Makes sense. Maybe somewhat related to that thought, like it's related to an audience question. Do you use re-ranking in your retriever, or is that something that you would consider kind of fine-tuning or adding?
So in our process, we didn't add re-ranking. So I think we got like raw results from the dense retriever and use it in the language model. We thought whether we should add. We think it could potentially improve the performance, but I think it also introduced latency and other things, so we didn't add eventually.
All right. Yeah, makes sense. The next question I was going to ask is kind of more on like a very broad level. What are some like practical challenges in like using this technique, or things that you're still thinking about in terms of stuff to tackle for future work? I can personally say, I mean, I think I implemented it, a very basic version of LLM fine-tuning in LlamaIndex, where you just do some import the retrieve context, get back some relevant chunks, put it into the prompt and fine-tune the language model over that. But between both the LLM fine-tuning as well as retriever fine-tuning, and you mentioned some of this in the results too, like what are some challenges with the current approach that you want to tackle in future work?
Yeah, so I think so for I mentioned some future directions, but one thing I think we should be careful is like, so whenever we can conduct fine-tuning, so I think there is potential of like it is kind of like depends on the purpose. So if the fine-tuning is like the output model is catering for specific tasks, I think usually like there's less to be concerned. But if like you want to fine-tune the model, but also want to maintain the overall capability of the model. So I'm just like going to like adding retrieval augmentation capability to a model which is already multitasking and serve other purposes. Basically, like you want to be careful about the task selection and also like how the fine-tuning is conducted so that I don't regress too much on the other tasks. So I think that's actually one thing which is interesting because so in our paper, we basically fine-tune over knowledge-intensive tasks and we basically test mostly on knowledge-intensive tasks. We didn't like try situations, for example, scenarios where you already have an assistant running there and now like you are adding like this type of fine-tuning. Does that make the assistant regress? So I think yeah, so I think things like these are probably like challenges I could think like when applied to real world application. And like I was saying, so we also found that like for retrieval fine-tuning similarly. So if you fine-tune using some outdated data sets where like it contains like outdated queries and other things, it could potentially hurt the model's generalization capability.
Yeah, interesting. The next question from the audience is, can tabular data benefit from the radit approach to retrieve like information from structured data? I'm actually curious if you thought about that. I think I need to noodle on this thought a little bit more to frame the question in the right way.
I think I probably understand the question. So I think it's a very interesting question. I think the short answer is I believe it can. However, I think how we achieve that could be a little bit more complicated. So I think retrieval augmentation is one type of non-parametric model augmentation. And actually nowadays people look into a wider range of agent actions. We can interact with tools, we can interact with APIs, and in terms of tabular data, people sometimes think of tabular retrieval as like we can issue SQL queries and get information from the database. So from this perspective, if we see this as like basically issuing a SQL query as a particular action, then like I think it's yeah. So recently there came out this type of like agent action fine-tuning approaches. So I think it can be applied here. I think another interesting question is like, I think sometimes people try to also add neural models on top of tabular data. But I think, so I'm less thought through in that scenario, but I think that could also be an equally interesting scenario. So where you might have a neural model on top of your tabular data, and then like you get something from it.
And related to that thought, have you, you might have mentioned this in the experimental results, have you thought about the relationship between like RADit and like agent like approaches, like chain of thought, like tool use, that type of stuff? Like can retrieval augmentation fine tuning actually benefit like agent reasoning?
Yeah, so I think I recently have been thinking about that a little bit. I think so I think especially lots of people working in the agent space actually sometimes just see retrieval as a tool. But I also think that view has a slightly different from retrieval-augmented model, our approach, and especially if we think about like the retro approach, where you have like you will have like parametric memories, and you have like the memory coupled with the language model through cross attention. So I think I feel like things are on a spectrum, and like you see like I think maybe they differ from like how interpretable you model the retrieval the memory or content. And so I think this is a vague relationship in my mind, and I sometimes feel like maybe tool usage perspective of like retrieval calling is more similar to how human browse the internet and perform actions, but like for like retro style or like these like pure RALM architecture, they were a little bit more similar to I have a mechanism just augmented the memory of the model.
Yeah, this is a very interesting question. I think that maybe at a very high level, the way I kind of think about it is there's stuff that's kind of like intrinsic to you. Like if you think about a person, they have like a brain and that's memory. And so that aspect is like learnable and differentiable. And so that's kind of like the retro approach where like the memory and retriever is coupled with the reasoning capabilities of the language model. And so that thing you can like backprop through. But then there's things that you can't backprop through, which is the like if you as a human use like Wikipedia as a tool, right? That's just an interface to query like some data. And so basically I think it's interesting, like maybe there's certain retrievers that are tunable because that's kind of part of your overall like state and memory that you can learn. And then there's also like you can combine that with tool use of things that aren't tunable because that's like the external world because you're looking up information. And somehow maybe you can fine tune the language model itself on top of both of these like data sources to try to like better use information. Yeah, I mean it's interesting. I'm not really sure. It's just like the kind of like rough framework that I have in mind.
Yeah, I think that's a good way to put it. And I feel like so I think this framework has different difficulty to be learned and to be set up. So I think sometimes like people also go for architectures which are actually simpler to implement if they can give like equally competitive approaches. Performance. So for example, like if like simply calling a tool like is usable, so why not, right?
Makes sense. Okay, I think that basically wraps up the questions as and we're nearing the time as well. So yeah, thanks so much, Victoria, again for a great presentation and taking the time to do a Q&A. I think it's just a lot of great stuff in here, and then the recording and all the materials will be shared on our YouTube channel as well. So make sure to check it out.
Thank you for having me.
Thank you. Bye, guys.
Thank you.